Definition and properties of scalar multiplication. Welcome, everyone. Today, we are diving into an essential concept in vector algebra. As you progress in your studies, you'll find that we often encounter situations where we need to modify a vector. Perhaps we need to stretch its magnitude to make it longer, or perhaps we need to flip its direction entirely, all while keeping it on the same line or orientation in space. To do this, we use a specific mathematical operation known as scalar multiplication. Over the next few slides, we will break down exactly what this operation is, how it affects a vector's direction and length, and how you can apply it to real-world scenarios. Understanding the basics. Now, before we dive into the actual operation of multiplication, we need to make sure we are clear on the two fundamental components we are working with. First, let's look at the vector, which we will denote as A with an arrow on top. Remember from our introduction that a vector isn't just a value. It is a quantity that possesses both magnitude, which is its length, and a specific direction in space. Second, we have the scalar, which we represent by the Greek letter lambda. Unlike a vector, a scalar is simply a real number. It has magnitude, but it lacks direction entirely. This could be any number you're familiar with, such as 2, -5, 0.5, or even pi. So how do these two interact? Here is the formal definition. When we take our vector, A, and multiply it by the scalar, lambda, the result is a brand new vector, which we write as lambda times A. One very important property to note here is that this new resulting vector is considered collinear to our original vector, A. In simpler terms, this means the new vector will always lie along the same straight line as the original, or perhaps along a parallel line, but it will never deviate from that linear path. As we move to the next slide, we will explore exactly how that scalar value can change the direction of this line. Effect on direction. Now that we have established what a vector and a scalar are, let's look at how the scalar actually changes the vector. As you can see on this slide, the direction of our resulting vector, which we call lambda vector, depends entirely on the sign of the scalar lambda. Let's break this down into three specific cases. First, case 1, a positive scalar, where lambda is greater than 0. If the scalar you are multiplying by is positive, the resulting vector, lambda vector A, will maintain the exact same direction as your original vector. A, for instance, if lambda equals 2, the vector is stretched to twice its original length, but it continues to point in the same direction. Next, we have case 2, a negative scalar where lambda is less than 0. This is a crucial point to remember. If the scalar is negative, the resulting vector, lambda vector A, will point in the opposite direction to the original vector. To visualize this, imagine if lambda equals -1. In this scenario, the vector maintains its original length, but it flips to point in the exactly opposite direction. Finally, case 3, the zero scalar, where lambda equals 0. This is a very straightforward case. If you multiply any vector by 0, the result is always the null vector, which we denote as 0 vector A equals the 0 vector. Essentially, the vector loses all magnitude and direction. Keep these direction rules in mind, because in our next slide, we will discuss how the scalar affects the magnitude or the length of the vector. Effect on magnitude. Essentially, the magnitude of our new scaled vector is simply the product of two things: the absolute value of our scalar and the magnitude of the original vector. If you look at the mathematical formula on the screen, it is expressed as the magnitude of lambda vector A equals the absolute value of lambda, multiplied by the magnitude of vector A. I want you to pay close attention to that absolute value sign around the lambda. As we will see in our upcoming real-world example, this is crucial because a length can never be negative. To make this easier to calculate, I've provided a simple three-step breakdown. First, you start by finding the magnitude of your original vector, which we call magnitude of vector A. Second, you find the absolute value of your scalar, which is the absolute value of lambda. Remember, this step is what ensures our final length remains a non-negative value, regardless of whether the scalar was positive or negative. And finally, you simply multiply these two values together to arrive at the magnitude of your resulting vector. Now that we understand how the scalar affects the direction of the vector, let's move on to slide 4, where we look at the effect on magnitude, or the actual length of the vector. Once we've mastered this calculation, we'll apply it to a practical scenario involving the velocity of a moving car in the next slide. Real-world example: velocity of a vehicle. Imagine a car traveling toward the east. We can represent this motion using a velocity vector, which we'll call v vector. First, let's look at scenario A, where the car is increasing its speed. Suppose the car doubles its speed, but it continues to drive toward the east. In this case, our new velocity is 2 times the v vector. Let's break this down using the steps we discussed in the previous slides. Step 1, our scalar lambda is equal to 2. Step 2, because 2 is a positive number, the direction remains unchanged. It's still pointing east. And finally, step 3. Applying our magnitude rule, the magnitude of 2v vector is equal to 2 times the magnitude of the original v vector. The vector has been stretched, but the orientation is the same. Now let's consider scenario B, which demonstrates a change in direction. Imagine the car suddenly hits the brakes, reverses, and begins moving west at the exact same speed. We can represent this new velocity as negative v vector, which is the same as saying negative 1 times the v vector. Let's apply our analysis again. Step 1, our scalar lambda is now negative 1. Step 2, since negative 1 is less than 0, the direction flips, it shifts from east to west. Step 3, when we calculate the new magnitude, the magnitude of negative 1 v vector is equal to the absolute value of negative 1, multiplied by the magnitude of the v vector. Since the absolute value of negative 1 is just 1, the magnitude remains exactly the same as our original speed. The length hasn't changed, only the direction. Now that we have covered the theoretical rules for magnitude and direction, let's put everything we've learned into a practical context. To do this, let's look at a real-world example involving the velocity of a vehicle. As we move to our next slide, we will summarize these key takeaways to ensure you have the core principles memorized. Key takeaways. All right, class, we have covered a lot of ground today, from the basic definitions to the practical application of velocity. Now, let's bring everything together with our key takeaways to ensure you have a solid grasp of the core principles. First, let's revisit the concept of collinearity. Remember that when we perform scalar multiplication, the resulting vector, lambda vector A, is always collinear to the original vector. This simply means that no matter how much we stretch or shrink the vector, it stays on that same line or a parallel path. Next, let's summarize the direction rule we discussed earlier. It is quite straightforward. If lambda is greater than 0, the direction remains the same as the original vector. However, if lambda is less than 0, the direction flips to be exactly opposite. Moving on to the magnitude rule, this is a crucial point for your calculations. The length of our new vector, which we write as the magnitude of lambda vector A, is equal to the absolute value of lambda multiplied by the magnitude of vector A. Always remember to use the absolute value of the scalar to ensure your resulting length is never negative. Finally, don't forget the special case of the null result. As we saw in our earlier slides, multiplying any vector by the scalar 0 will always result in the null vector, which we denote as 0 vector A. Keep these 4 points in mind, as they are the foundation for everything we will do next. In our final slide, I will highlight a few common pitfalls that students often encounter when working through these types of problems. Common mistakes to avoid. First, let's talk about ignoring the absolute value. This is a very frequent error. You might be tempted to write that the magnitude of lambda vector A equals lambda times the magnitude of vector A. However, this is mathematically incorrect because, as we discussed in the previous slide, magnitude represents length, and length can never be negative. For instance, if our scalar lambda is equal to -2, the magnitude of the resulting vector is actually 2 times the magnitude of vector, not negative 2 times the magnitude of vector A, always remember to apply that absolute value to your scalar when calculating length. Second, please be careful not to confuse scalar multiplication with the dot product. It sounds similar, but the components are fundamentally different. As we saw in our earlier slides, scalar multiplication involves a single real number, a scalar, and a vector. In contrast, the dot product is an operation performed between two different vectors. Keeping this distinction clear is vital for your work in vector algebra. Finally, watch out for direction confusion. When working with negative scalars, it is easy to focus only on the change in length and forget the impact on orientation. Remember, a negative scalar does more than just scale the magnitude. It fundamentally flips the direction of the vector by 180 degrees. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. Even if you feel you understand the concept, these are the specific areas where students often lose marks in exams. If you can avoid these 3 mistakes, you will have a much stronger grasp of how scalar multiplication operates in space.